Okay, so now we're live. Um, okay, so let's return to where we were last time, which was figuring out how to do subtraction without doing subtraction. So what we remembered, right, when we did two's complement was that the negative of a number, the procedure for getting the bit pattern that represents that negative number is to take your original number, flip the bits, and add 1. Right? So if I wanted to do, for example, 5 minus 3, I'd write down the bit pattern for 3, I'd flip the bits and add 1, and I'd get some resulting bit pattern. That bit pattern represents minus 3, and I'm going to add that to the other number, right? So I'm thinking of subtraction as really being addition of a negative, okay? All right, now, the other thing that we figured out was adding 1 to a number is easy, right? We've got an addition code. We can load in the number 1 to a register, so we can definitely add 1. Great. The flipping the bits part required a little bit of thought, but we cracked it. What was the trick? Yeah, we used an exclusive OR with a bit pattern of all ones, right? So that combination of taking the number, the bit pattern, so in this case it'd be the bit pattern for 3, XORing it against all ones, will do the flipping the bits part, okay? So, and then we can add 1 to that result. Okay, so now what we want to do is let's look at the code necessary to do this, okay? Okay, so if I want to subtract 2 numbers from memory, let's, like before, okay, let's see, where am I here? Okay, yeah, here we go. So let's load, let's just start by negating a number, okay? Just get that piece working, and then we'll throw in the addition to it. Okay, so let me load a number from memory into register 2. Okay, fine. And then I also need to load the bit pattern of all ones, right? Because I need to use that for the flipping business. Well, what is the bit pattern for all ones in hex? FF. Okay, so that's why I'm going to load FF into a memory cell. And in fact, you know what? Let me just use, let's just do this right. Okay, so let's load the 2 numbers from memory. So let's just go for the kill and do subtraction. Okay, so let's assume here okay, so we want to compute the difference. So we'll take whatever's in FE and subtract it from whatever's in FD. Okay? All right. So first thing, we need to get the 2 numbers in memory. So let's load register, let's say 1 with the first number. Let's load register 2 with the second number. Sound good? Okay. And then we also need to load 2 bit patterns. We need the bit pattern of all ones, which what did we say that was? FF and hex. So I'm going to do this. Okay. Why did I put a hashtag there instead of a $? The specific number, I'm not going out into memory cell FF and seeing whatever I find there. I want the actual number FF. Okay? Good. And then similarly, I also need to load the number 1. So that when we flip the bits, we then need to add 1. So I'll go ahead and get that loaded. And that's all that we need to load in. Okay, so I need to XOR register 2's contents against register 3's contents, and I need to put the answer someplace. Okay, where would be a good place to put that partial answer? Register 5 seems like a good enough place. Okay, so I'll exclusively OR registers 2 and 3 and put the partial answer in register 5. Okay? Good? All right. Then, so register 5 has the flipped bits version. I then need to add 1 to it. Okay? So I need to add registers what and what? Registers 4 and 5. And I want to put the answer where? We could put it in register 6. I'm just going to put it back in register 5 because I don't need the flipped bits version for anything other than to then add 1 to it, right? So there's no point in keeping the flipped bit version without the extra 1 laying around, right? That said, yes, if you want to store it in register 6, that's fine, okay? But how many registers have we used if we do that? 6. How many do we have? We only have 16, and register 0 is a little bit special. We'll talk about how and why later. So in some sense, you really only have 15. That sounds like a lot, but for a really complicated program, you run out of them eventually, no matter how many you've got, okay? And so what eventually happens is you have to start reusing the registers, and that's where it can get confusing because you have to kind of keep track of, okay, at this part of the program, register 0 is being used for this, but down here it's for something else, okay? We'll get to that later. All right, so we do the addition. That gets, so now R5 has the negative of R2. Okay, so what were we wanting to do? We were wanting to do the subtraction of what's in register 1 minus what's in register 2. Register 5 has the negative of what's in register 2. So what do I want to do? Add registers 1 and 5 and put the answer where? 5, or I'll go ahead and put this one in 6. Because maybe we still need to know what the negative is for something else, right? Okay, is that okay? So, all that will do then is this actually does the subtraction. Right, so if we had two numbers and we were trying to think of it as doing A minus B, then what we've really done here is A plus negative B. Okay, good? All right, so then what's the final operation that we probably want to do? Yeah, so show the answer. So let's store the answer, and let's put it in memory cell FF like we have done with our previous programs. Okay, and then we can halt. Okay? All right, good? So the next thing we need to do is we need to translate this into the machine code so that we can put it in our little simulator and run it and make sure everything works. Okay, so for that, of course, we need the table. All right, and so let's take, let me split screen this. I'll try and split screen this if Linux will cooperate. Unlike Windows, at least on this version of Linux, there's not like one of those magic auto split screener. Yeah, there's probably an app I can get that will do that, but, um, okay, so let me get rid of the file browser so that we can see a little bit better. Okay, so we need to just translate all of these things. Okay, so what's the first one? We're loading a register. So which of the two opcodes is it? Opcode number 1 or opcode number 2? 1. We're going into register 1. We're coming out of memory address FD. Okay, so this will be 12FE. This will be 23FF. 2401. XOR is 9, so 9523. 5545. 5615. 36FF. C000. Okay, so does that match everything on the table? Did I F it up? Look okay? Well, yeah, we'll find out, obviously, but does it look okay from the table? Okay. All right, so I've got all of the machine instructions listed down, and now what I need to do is, in order to use this with the emulator, I'm going to just take all of them, all of each individual machine instruction, and just make one big long single, put them all on one line, basically. Okay, and you'll see why that'll be useful in just a second. All right, so let me redo it. Okay, so 11FD, 12FE, 23FF, 2401, 9523, 5545, 5615, 36FF, and C000. Okay? All right, so the reason I did that is because I'm going to take that big string of all of it, and I'm going to copy that, and then we'll go over to our simulator. Okay, so good, because I want to full screen the browser. Okay? All right, good. All right, so I've got all of the machine code, and now let's go to the Brookshire machine emulator. And what I'm going to do is, in the URL, if you put a hashtag and then you paste in your code and then refresh the page, all of our code has been loaded into memory. Okay, so that way you don't have to go and type each part into each individual box, because that's kind of a pain, right? Okay, but what we do need to type into the individual boxes are the two numbers we wanted to actually do the subtraction with. Okay, so what numbers do you guys want to do? 8 and 5. Okay, sounds good. So 8 there, 5 there, and let's clear it and run it. And so, of course, we should end up with 3 when all is said and done. Et voila. Okay, so it worked. And for that matter, let's test another number, because what would happen if I subtracted a negative? It would be the same as doing addition, really, right? Okay, so let's take, for example, here the number FB, right, which represents -3, yeah? And let's put it here. Okay, now one thing I really like about the emulator, but also really dislike, is if I hover over a memory cell, what does it show me? Yeah, it'll tell me it's which memory, or which address I'm in. I'm in memory address FE in this case. What's the hexadecimal value that I see? Well, it's FB, okay? What is FB in binary? And what does FB represent as a signed integer? And then also, what does FB represent as a Brookshire float? Okay, ignore the float. It's wrong. Okay, I think I mentioned this last time, but in Brookshire's book, when he defines floating point, he doesn't have the hidden one. Yeah, so his standard is not IEEE 754 compliant, and so the numbers that that they decode here to are not the same as what we would decode them to. It's using a different standard, so just ignore them entirely. Okay, you're looking sus about that, Thomas. Yeah. Huh?
Yell at this guy.
Well, okay. Yell at who? Joel or Brookshire? Both. Okay. Well, Joel just did what was in the book to match what was in the book, right? No, he did, right? Well, okay, let me back up a minute on this whole floating point standard. When was IEEE 754 first actually ratified? No, it's in the 80s, like 84, 86, somewhere in there. Okay, so up until that point, there was no broad universal standard for how floating point numbers were stored. Okay, so it would differ potentially for different manufacturers. Now, they all used essentially a sine exponent mantissa kind of idea, right? That's just logical, but they didn't all necessarily use the same number of bits for each part. They didn't therefore use the same bias for each part, right? It depended. Okay, so for example, the internal to the I think it was the first Intel's first floating point coprocessor. Internally, it actually did everything in like 80 bits, but it only returned either 32 or 64-bit answers. And the idea was it would use those extra bits for extra precision while it was doing computations, but then just return a 32-bit or 64-bit value. I think I've got that right. But point being that it wasn't standardized. Okay, so now when Brookshire, I mean, he's on like the 13th edition of this thing right now, of his book, right? So when the first edition was published, I mean, heck, it could have even been before IEEE 754. Actually, don't know. I need to go, yeah, look it up and see when he published the first edition of it. It'd be interesting. Okay, so anyway, and if he or his co-author happen to be listening to the stream, or if anybody happens to be listening who's in computer science at Marquette University, because that's where both of them are, in the 14th edition, can we please make it IEEE 754 compliant, just for everyone else's sanity? Thank you. Okay. Yeah, but there, like I said, there was no standard in the up until the early to mid 80s. Right now, I just want lots of Gatorade. I've been really dehydrated the last couple of days. I don't know why, but yeah. So I've been drinking water and Gatorade like fish. Yeah. So anyway, okay. So yeah. So ignore the float decoding. Just it's not correct. And the simulator that John and Owen have been working on will be compliant with it once we get everything running. But we're not there yet. So, okay, so what we were going to do, we were going to do 8 minus -3, and so we should, of course, get 11, but how am I going to see 11? OB. Right? Because it's in hex, right? So I'm not going to see 11 in the memory cell. What I'm going to see is OB. All right, so let's rerun the thing. And right now we still have 3 from the previous computation, but it's going to get overwritten here in a moment. Oh, sorry. Yeah. Okay, so what we actually did here was 8 minus a -5, not -3. My bad. Yeah, I misspoke. Okay, and so we get D instead of B. Yeah? Okay, is that correct? Well, yeah, because here, that's -5, so I did 8 minus a -5, and I got 13, which is 0D, of course, in hex. Okay, so it worked. Yeah? Okay, so subtraction, not too bad. Okay, now that said, right, in version 2 of the processor, or my version of it, opcode 6 will do that in one single operation. Okay, but it doesn't exist yet in the emulator or in my circuit version of this processor, because that's what I was working on this summer, is actually designing the circuit to be this processor, and then getting it working on what's called an FPGA, with the goal eventually to actually fabricate it in real silicon and actually have a chip that's this processor, which is kind of crazy if you think about it, but hey, why not? Okay, so let's look at, we did our subtraction example, and let's look at, we'll do what's called bit extraction, but we're going to do it in order to also look at, we'll start to look at what register 0 gets used for, and how, so everything we've done so far is just a glorified calculator, really, right? What truly makes a computer is the ability to do conditional statements, right? If one thing is true, do this, otherwise do that. Yeah? That's what makes a computer. Because if you have an if kind of construction, you can build loops out of it, and if you've got conditionals and loops, you have a Turing-complete programming language, okay? And as you guys are hopefully figuring out with bare bones, you can actually have a loop construction and build an if out of it rather than the other way, right? But if you have one of them, then that's enough to be Turing complete. And if you have sort of a bunch of different versions, that just is more convenient, okay? Okay, so how do we know if a number is negative if we look at its bit pattern representation? Yeah, so if the first bit, the far left-hand bit, if that's a 1, then we know that the number is negative, okay? If it's a 0, we know that the number is not negative. And I notice I did not say positive there because it could be 0, right? Okay, so it's non-negative, which means it's either 0 or positive. Now, 0 ought to be obvious because it's just all zeros. But yeah, okay. So let's write a program that's going to do the following. It's going to load a number out of memory, and then we want to have the program determine, is that number positive or negative? Okay? All right. Or let me say it this way. Is it negative or is it not? Okay, just because we could put 0 in. Okay, so what I'll output is, well, what do we want to output if the number is negative? Well, I mean, that's up to us, but what makes sense? How about a 1, okay? It is negative. And if it isn't, what would we output? How about a 0? It's not negative, okay? Now, we could output 17 and 35. Why would we? Right? Because we can, right? But there's no, there's no reason that we would choose those numbers. 1 and 0 just make more sense, frankly. Okay? It's sort of thinking of 0 as representing false and 1 as representing true. Okay, make sense? All right, so let's write this thing in order to do that. All right, so let me go back into here, and let me full screen it for now. And let me close some of these others. Stuff from my other class. Okay, and let's make a new file, and we'll call this one detect negatives. Okay, so two things I'm going to do a little bit differently here, and you'll see in just a minute, is, well, okay, first thing, we want our program to load FE into memory to check whether it is negative or not. What's up? Huh? What, is he trying to slip something in your water or something? I mean, too soon? Yeah. It is, yeah. But yeah, don't do that. Speaking of which, right? Interesting email from Reading about the original T-shirt.
Yeah, we've heard that.
Yeah, like.
Someone made it anyway. I think someone at Davis signed it. What about the duck for pause guy? I had a lot of people who this year.
Yeah. Maybe he graduated. I don't know. Right. So, yeah, think before you design T-shirts, right? All right. If negative, put 01 in FF. Otherwise, put 00 in FF. Okay, so that's what we want our program to do. Yes? Okay, so the first thing I've got to do is figure out how do I do something that's going to get me a binary decision making capability for checking whether or not a number is positive or negative. So as humans, what did we say you do? You look at the far left bit. That's all you got to do. Okay? But we can't just tell the computer, look at the far left bit. We have to have something that uses the operations we have at our disposal. Okay? So what we're going to do is a variation on what we did with our XOR trick. Okay? Which bit position do I care about in this case? The far left one. Okay? So what I'm going to do is I'm going to load this number. Okay, let me put a space there just so it's easier to read. And so the trick with what we did with the exclusive OR thing, right, for flipping the bits, there were really two pieces to the trick. One, which logical operation did we use? Exclusive OR in that case, okay? And we also had to choose a bit pattern to use with it, right? So two things were required. So here, I claim that we want to use this bit pattern, okay? 1 followed by all zeros, okay? And why? Well, which bit position do I care about? The far left one, okay? So I put a 1 in that bit position and a 0 in all other bit positions that I do not care about, okay? Which logical operation do I want to then use? Okay, so what operations do we have to work with? Add, subtract, and inclusive OR and exclusive OR, right? And there's also a bit rotation, but all that does is move where the bits are, so that's not going to work. Okay, so of those, let's think about them. Which one is going to be the one that we want? Thomas, keep your mouth shut because you spoiled it last time. I'm going to cast mute on you. Yeah. Okay, any ideas?
I mean, we can just add because they could do.
Okay, it's not add. Huh? It's not the or either. It's and. Okay. All right, unmute. So why is it and? Okay, well, let's think about it. So let me just choose a random number. What was the number that we had last time? FB, right? Which would be F and B represents 11, so that would be an 8, no 4s, a 2, and a 1, right? Okay, so this number clearly is negative. So if I do, well, okay, let's just say I added them, okay? And let me just work this out on the chalkboard just for a quick arithmetic's sake.
That number is negative, you said?
Well, both of them are in this case.
Because there's the 1 at the start?
Yeah.
Okay.
Right. So I chose like the second number, FB, right? That represented -5. That was the number that we had in our previous example. Yeah, let's take that one out of essentially randomly. This number will always be the same for our purposes. Okay, so let's say though that we add them. Okay, we're gonna get, who knows what we're gonna get, right? In fact, we could get, well, I mean, we could work out, actually, I don't need to work out what it is, right? We could work it out, okay? But we're gonna get some answer. Now, if you changed the number, the second number, would we get a different answer? Yes, okay? And if you changed it to yet a third thing, we'd get yet a third answer. That's not gonna work, right? We need something where we only get 2 possible answers out of this. Okay, and why 2? Because we need to make a binary decision, yes or no. Okay? Okay, so do you guys see that add is not gonna do it. Okay, and is the one that we want. Okay, and let's think about why. If we and anything against a 0, what are we gonna always get?
0.
Always get a 0. And that's good for the far 7, the right-hand 7 bits, because I don't care about them. Right, so just kill them. Okay, kill them all. Okay, but which bit do I care about?
Far left.
The far left bit. Okay, so if the far left bit of the number we're examining is a 1, and we and it against a 1, what are we going to get?
1.
And if it's a 0, we get
0.
right. So there's only 2 possible outcomes. Okay, so if we and our number against 1 followed by all zeros, we get exactly 2 possible answers. Why does my phone keep buzzing? Oh, it's Dr. Gelman, which could be a, oh. Sorry. She has there's a poli-sci candidate on campus, and when she texts me, when she calls me is when it's an emergency, right? So she called me. This maybe presaged the shit show that was the academic year of 1920. Okay, because in fall of 19, it's the night before classes start. We'd all gone out to dinner for our last supper, if you will, right? And it's like 10 o'clock at night. I'm starting to think about getting ready to go to bed and, getting things ready for the morning. And she calls me. She never calls me, right? We just message on Facebook or whatever. So she calls me and she says, there's an effing bat in my house. And I'm like, I'll be right over. Okay. So I go over there, and by the time I got there, the bat was gone, right? And so I'm looking through the house, everywhere with a flashlight, bat's gone. Okay, whatever. So then, this is maybe 3 or 4 months later, she calls me. And I answer, and I said, let me guess, there's a bat. And she's like, yep, I'll be right over. So anyway, yeah, we had, I think, 3 bat incidents, and then finally she got a hold of somebody that does bat removal and goes through the house and finds all the little cracks and stuff where they can get in and seals it up with foam and stuff. So we haven't had any bats in a while, but yeah.
My house has had 2 bats and the birds kiss into it for me.
Yeah. So, okay. Anyway, so what?
Just seals up enough that you can't start a fire, so it's useless stuff if everything's all.
Right. Okay. So when we do this with and, we get exactly 2 possible answers. Either all zeros, okay, which would mean that the leading bit of the first number was a 0, or we get a 1 followed by all zeros, in which case the leading bit was a 1. That means we have the basis to make a binary decision. Okay? So do you see how the trick works here? So, yeah. Now, by the way, I'll just mention this because it's going to be a good exercise. What would what would happen if we looked not at the far left bit, but at the far right bit? What does it tell us? Whether it's odd or even. Yeah, because it's the ones place. Okay, and all the other bit positions are even powers, right? Because powers are 2, but they're all even except for 2 to the 0, which is 1. Okay, so the far right bit tells you the parity, which is what we call whether it's odd or even. And the far left bit tells you whether it's positive or negative. That's kind of cool. Yeah? Okay, so let's get this set up to do the ANDing. So first thing we need to do is just load in the number. Okay, and so we need to load in, let's put it in register 1, and we'll do, where is it coming from memory? Memory cell FE. Yeah? And I also need to load in the number that's 1 followed by all zeros. Okay, but I have to write this in hex. What is 1 followed by all zeros in hex? 80. Good? Do you guys agree? Okay. Okay, and now we need to do the ANDing operation. Okay, and we're going to AND registers 1 and 2, and where are we going to put the answer? How about register 3? Okay. So where is register, what is the AND opcode? It is, let's go back up to our table. AND is operation number 8. Okay? So we'll do AND register 3 with 2 and 1. Okay? All right. Now is where we have to do the decision-making thing. Okay, and so let me just save this, and let's go back to our note document. And let's look at this operation. Okay, operation number B. Okay, it's coincidence that it's B. What's the mnemonic that I've chosen for it? BEQ. Okay. In Brookshire's original, like in his book, he calls it jump. That's also a good choice for this. And so when I started doing this, I actually had the mnemonic of JEQ for jump. But then I decided to change it to BEQ. And the reason is because it's a branch. Okay, that's one way that you can call this binary decision-making thing. You're branching to either one path or the other, right? And in a sense, right, a program is a bunch of, like, you're going down the path through the forest, and you come to a junction, and you either go left or right, right? And if you go left, you do some things. If you go right, you do some other things. And maybe the paths come back together eventually. Right? That could happen. Or maybe they branch even further. Okay? So, the branching, okay, is the way this works is you compare a register to register 0. Okay, and this is why I said don't use register 0, because you have to use it here. And so think of it as sort of being somewhat special. Okay, so I have to compare a register's contents with the contents of register 0. And those two contents can either be the same or not. Yes? And if they are the same, then what I'll do is change the program counter to a new value, which will be a new place in memory where there's code to execute. And if it's not, then I won't change the program counter, and I'll just go on to the next instruction. Okay, so that's what this thing will do. So I called it BEQ for branch on equals. Right? And does that pretty well describe what it does? Right? We branch, so hang on one second, Thomas. So think of it this way. You've got your path through the forest, and you come to you're going this way, but then there's a T and there's a path that goes to the right. And you're deciding, do I branch onto this new path or do I continue on the path that I'm already on? Okay? If the register's contents are equal, you branch. Otherwise, you just keep going. Okay, does that make sense? Okay, Thomas, your question.
Does this mean that there are some programs that would need multiple halt commands?
Yes. Okay, or you could branch all of them to one halt command at the end. Okay, both make sense. Okay, now, and I'm going to get to that in a second. So let me finish just briefly, and we'll have to pick up with this on Monday. But how can I guarantee that a branch will always happen?
Maintain 0 for all?
Yes, I'll compare register 0 to itself. Because no matter what's there, it's equal to itself, right? So if I want to force a branch, okay, sort of an unconditional branch, then I'll just compare register 0 to itself, okay? Which is how you can get around having to do have lots of halt commands throughout the program. You can just have each different piece all jump to one halt command at the very end, right? 6 of one, half a dozen of another. Okay, so let's see. Was there anything else I wanted to say on this for right now? Okay, so the reason I called it BEQ, other than it's fairly descriptive about what it's doing, okay, is in real assembly languages, there are actually more branching instructions. So there's a branch on equal. In a lot of them, there's also branch on non-equal, okay, which in those languages, the mnemonic is BNE for branch on not equal, okay. So I chose BEQ here to make it, again, look like real assembly languages of the day. Okay, so we'll have to pick up with this on Monday, and I'm going to hand back your things on Monday. I forgot to put them in the computer yesterday. So anyway, pay attention to Canvas for a flurry of updates, and I'll see you guys Monday.